Right. Good morning, everybody.
Good morning.
It's fun to be back on this stage in particular. I love this venue. This is probably the quirkiest place I've ever attended or spoken at a conference, and it's just awesome. So thank you, Alex, for bringing us back here again. So my name is Tim Ewald. I'm the CTO of Kevel. I'm joined on stage with our Senior Director of Research, my friend and colleague, the notorious PDG, Paul deGrandis. And we came today really to tell you a story about a problem that we started grappling with six and a half years ago, and how we have gone about working to solve it over that time. And that talk is Immutable Values in the Big Wide World. So if you read the abstract for this talk, I made what might have been a bold claim, and I thought about leaving that for late in the talk as a conclusion, but I decided I'd throw it out here. I believe that much of the kind of industry standard thinking about what cloud architectures are about is incorrect. Loads of folks would say it's about lambdas and serverless. I think that's wrong. They're super expensive. Amazon Prime published a white paper last year about moving off AWS lambdas and reducing their costs by 90%. In terms of our support issues or concerns with running on the AWS platform, in the last 2 years, the single most significant issues have been Lambda dispatch problems in US East 1. So we make some use of Lambda, but we avoid it where we can. A lot of folks would say Kubernetes. I think Kubernetes has its uses, but it's also super complicated. I'm just real curious, how many of you deploy systems on Kubernetes?
This is dangerous. Yeah.
Just real quick, how many of you operate the Kubernetes clusters that you deploy your systems on top of?
Oh, yeah, that's perfect.
Right. There you go. So I think there's a much more interesting way to look at the world, right? And this is a lesson that I learned working on the Datomic team, and I'll talk more about that in a little bit. But I think the most interesting direction for cloud systems is to leverage the fact that we now have infinite ubiquitous storage. You know, every compute service is attached to a data plane that you can store massive amounts of data on. You can have different performance and price characteristics on AWS with Dynamo, EFS, and S3. But that's a resource that we've never had before in our data centers, and we should use it. The other thing is we now have access to just absolutely massive machines, and we have language runtimes that can use massive amounts of memory. Paul dug up a quote a while back that I really loved, which was just a reminder that, you know, distributed computing was an approach to solving problems that you couldn't solve on one machine. And we have some really big machines now, right? And leveraging that, leveraging the memory, like nothing's faster than that. Solving problems on big machines gives you just a tremendous amount of power, capability. So we are responsible for designing, building, and operating the Kevel platform. Our business, we are a SaaS company that's a service provider. We build services to allow companies to build their own ad programs. So we focus on enabling companies that want to generate revenue from ads to do so without buying into all of the big ad tech, Google, Meta, surveillance capitalism, and all the rest of it, right? It's about using data that you have, first-party data, to build solutions for your business. The platform is 12 years old. It was born on AWS. It's never run anywhere else. It's multi-tenanted, geo-replicated. It runs out of 10 data centers now around the world. It's focused on multi-objective optimization, tracking various targets that people have with ad campaigns. Today, it does several low-digit billions of decisions for people. P99 response time worldwide is 50 milliseconds. The decision engines run at 5 nines availability, and as I say, across 10 data centers. It's an always-on system. I've worked in the company for 7 years, like the thing's been running that whole time. One of the things that attracted me to this business, I didn't come from an ad tech background, but I wanted to work on something that was worldwide, entirely cloud-based, and didn't ever have a chance to be turned off, right? The engineering challenge in that was super appealing to me. So that's what we operate for our customers. And I want to talk a little bit about how we got here. That's really the point of this talk. We're going to jump around in time a little bit. We're going to start by going back to the system as it was in 2018. Then we're going to talk about, well, the problems in this system, where we've landed, and then we'll kind of talk about some of the steps to get here. So for any Whovians in the audience, it's going to be a little wibbly-wobbly, timey-wimey. But so this is the system as it existed. Sorry, I'm supposed to keep close to this mic. It's hard not to turn around. As it existed in 2018. And I'm just going to walk through it at a pretty high level. So we can talk about the basic pieces, how they work, and then that'll lead us into the problems with them. I know that names are super important in the Clojure community to pick ones that really capture the essence of the thing. So you're going to be learning about Geffian, Heimdall, and Bifrost. So our system, I'm actually going to start on the bottom, not the architecture piece, looking at the data model. So our system is comprised, at least in this scope, of two things: a management system that allows you to configure the platform to do what you want, and a delivery system which is actually making decisions for you and then capturing events that are the result of those decisions.
You can think of it like a globally distributed database. That delivery system is just handling queries all around the world. Yeah,
absolutely. So the management system, for ease of use of our customers, has a hierarchical model that they manipulate. So they create an advertiser. Advertisers have campaigns. Those things have flights. They have ads, right? And it's done this way just to make it easy to think about, and it's just a natural model. In the delivery system, we do not want a hierarchical model because the cost of traversing the hierarchy at decision time is too high. So we take this data that's hierarchical in management and we denormalize it to flat records for the delivery system just for speed of lookup. I mentioned that we have lower than 50 millisecond response time. It's doing things like this that enable that. So a customer is making API calls to configure their set of campaigns and ads. Those changes are going through the management API into the management database. They have to flow through to the delivery system, and that's the role of this component, again, back in 2018, called Geffian. I have to keep saying it's back in 2018 for Craig, because if I keep mentioning Geffian, he's going to start having flashbacks, and it's gone now, Craig, it's okay. But back then it was here, and Geffian's job was to figure out the impact of a change that someone had made on that denormalized data set. So the most important one for this context is there's a bunch of reasons why a customer might want to deactivate a subtree in this thing. They might want to deactivate an individual ad, a flight, a campaign. So to know whether a given ad is active or not, you have to know the activity setting of everything up the tree. So if a customer says, I'm going to deactivate this campaign, it's got to ripple down to all of the records in delivery, right, that are denormalized that belong to that campaign. And it's Geffian's job to work that out. You'll notice Geffian has a queue above it, and it's using that to actually coordinate the tree traversal. So if you said, I want to change this campaign, that would go to Geffian. Geffian would say, oh, I better go look at the flights, and it would send a message to itself. And it would work its way down the tree, and ultimately, when it sorted out what set of ads needed to actually change, and it would be capturing data as it did this traversal about, we'll just talk about the active bit here, it'd be capturing that in order to tell Heimdall, hey, these ads need to be turned on or off. Does that make sense? All right, so Heimdall is doing three things in this system. It's maintaining the set of active ads, which it's stuffing into that Redis root. It's calculating what's called a balance weight, which I'm not going to spend a lot of time on, but it basically is if you set a goal for an ad of I want this to say, I want 30,000 impressions in 30 days, then the optimal path would be 1,000 a day. And based on traffic and competing campaigns and what have you, you're going to be tracking to that line or above it or below it. And the balancer is constantly adjusting a weighting factor to try to keep you and all the other ads that are being served, trying to keep them all on their optimal path. So it's doing ad set management, it's doing balance weighting, and it also, back in 2018, was building the index that we need to look up ads on the engines. And it's taking all of that data and it's pushing it into this Redis root. And so back in 2018, our mechanism for delivering data out worldwide to our decision engines is to push it into a Redis root that is replicated in a tree that goes around the world. This is not what Redis replication was designed for. We'll talk more about that in a minute. But it gets all the way down to actually land on the engines. There's a Redis replica on the engine, which might sound crazy, but that's how we get 5 nines, right? Those engines can be completely disconnected from everything internally, and they will still serve requests. So there's a lot of value in getting all the data you need onto the box if you can. That data is used when decision requests come in to find a relevant ad and hand it out. And then that ad is going to generate impressions and hopefully conversions, and those come back into the events API. That in turn runs through this thing called instant counts, which is gathering up data to feed into the balancer, Heimdall, and that's to adjust that weighting, right? So it's a feedback loop between decisions and events. All right. So there are at least 3 big problems with this. The first one is that if you go to the management API at the top of that tree and you deactivate an advertiser, it will cause Gephian to initiate a breadth-first tree walk of everything in that subtree, and it will do it all via a queue. So it's going to walk the tree, but it's going to do it by queuing messages to tell it to take the next step, and on each step, it's going to access the database, right? And it's going to just, once that process starts, it's just going to fill the queue with these messages. While that's happening, if in a user interface, the user says, oh, that was the wrong advertiser, reactivate them, guess what's going to happen? It's going to kick off another depth-first, or breadth-first rather, tree walk through the whole thing with message queuing and the database to turn everything back on again. So we used to experience these things that came to be known as Gephian storms, which is somebody did something with our API or a UI that just caused a flood of messages in Gephian, causes that queue to back up, all kinds of things. So we used to have to run really enormous machine fleets to process that stuff, and sometimes it could generate like just a tremendous lag in how long it took to process changes through the system. The second issue we have is with Redis. We have a replication tree in single regions, right, spanning multi-AZs for high availability, but also spanning multiple regions. The thing about this is, first off, it leads to nonlinear cost growth. There's a maximum branching factor that you can have in Redis based on the amount of data you're pushing through it. And we need to dynamically scale our decision making, right, based on customer load. So a tenet of our system is if you choose us as the vendor for your system, then if you get really popular and your business grows, we need to grow right along with you. But we have this backing store behind us that also has to grow, and we can't just keep, sorry for all the sound up here.
It's a beautiful tone.
It's a protective cover that isn't registering my fingerprints. So to grow the Redis tree to service those machines, you need multiple tiers, potentially, right? So it's nonlinear cost growth, which is never a thing you want if you're a SaaS business. The other last problem is we're tied to an old version of Redis. The only way to manage the Redis tree in a reasonable way, you need to be able to get into the middle of it and prune and graft, right? If you get a note from AWS saying this machine that's part of your Redis tree is going to be cycled on this date, you have to deal with that. And in the older versions of Redis, the replication protocol was very flexible about allowing you to manipulate things in the middle of the tree. The newer versions no longer allow that. So we're pinned to an old version that will go out of support and security updates and the rest of it. So we have to get off of it. It's also a bottleneck for just how big we can go, right? This store is being used for the ad set and indexes. There's a maximum number of ads that you can put in there for a given customer. We tackle this across customers with sharding, so that picture showed one delivery system, but at the moment, I think there's either 5 or 6 to cover the load that we need for different customers. So there's challenges with Gephian, there's challenges with Redis. The last and most important problem is, while this system was totally reasonable for the load that it carried when it was initially conceived, our load has grown. We've been lucky in our business. Every year, some customer comes and takes us up an order of magnitude in some dimension. And what we found is that under heavy load, the system just is not deterministic. You can start with the rate at which changes come in, how they get queued, how many Heimdall, it was shown as one box, as Geffian was, but it's also processing a queue and is a fleet of machines. And so there's an ordering problem. It's possible with enough traffic that turning things on and off, you may end up with the wrong state in Redis. And Redis of its nature, right, it's not a transactional store. You could make it do things serially in order to ensure correctness, right? We could attempt to order all this stuff, but it will go crazy slow.
So transacting many, many millions of dollars plus non-determinism is bad.
Yeah, that's
quite bad. Quite bad.
Thank you.
Yeah.
As an example, right, I think the maximum load we've carried on Redis just from updates is 350,000 requests per second, right? So that's the kind of loads we're talking about for data flowing into the system and trying to figure out, how to coordinate all this stuff.
That's a single node. That's not across the cluster.
Right. So that's where we were in 2018. I had a hard time. I wanted to write this slide of very logically. This was the thought process we went through. The reality is we spent a bunch of time thinking about a whole bunch of things all intertwined, and I tried to tease them apart here. When I started working on this system, I had newly moved over from working on Datomic, right? And Datomic was interesting for a whole pile of reasons, but in the most abstract sense, it was really interesting to think about distributed systems through the lens of functional programming. And I took a big lesson away from work on Datomic, like Rich's observation that the architecture of databases that we live with today, including in Redis, is rooted in the economics of computing from the 70s, right? Where you had to have a big machine that you went to because you couldn't afford to put a lot of disk and a lot of memory in a lot of different machines. So you end up at this one destination that can do all this stuff, right? And we don't live in that world anymore. That's my point about ubiquitous storage and as many large or different size machines as you want, right? We have a lot more flexibility. And so in particular, thinking about that in this system, I realized there's really two functions that drive this whole delivery system. One is functions that act on changes to configuration, right? They produce a working ad set. And the other is a function, then that's the first one, but inside the delivery system there are two. One is the decision functions, and then the other is the balancing function, right? The balancing function is what was the old state of this ad in terms of its progress towards its goal? Have there been any config changes? Has it hit a cap? What have you? What should its new balancing weight be? And the decision function is just that. And all of the other information in the system is derived from those two things. And we could use this ubiquitous storage to model the state of the system as values, immutable values that we've stored off somewhere, right? So you could go through these functions, build up bodies of data that we would essentially snapshot. The second thing we spent a bunch of time thinking about was how to solve that Geffian fan-out problem, right? Sorry, I should have used that term earlier. That tree walk became known, just like Geffian storms, as the fan-out problem, which is you made one change and it fans out to some set of ads, and we have to be able to calculate it, and we have to be able to calculate it fast. Geffian clearly didn't do that. There was an intermediate attempt to build another data store that would keep all that data in a format simpler than the management database that we would be able to run a query against, but there too, the right performance to get that stuff in durably, and then the actual query processing load proved impossible to get, to make it capable of carrying the load that we needed to carry, right? So after sort of backburnering this question and just thinking about it periodically over months, it just became clear that we really need to solve this problem in memory. The thing that's going to make it fast enough is to build the set of indexes we need in RAM to be able to calculate it super quick. The motivation for it was a bunch of research into roaring bitmaps, which is one of our favorite data structures.
Beautiful.
And basically, the idea was you could keep a roaring bitmap of the activity switch, the activity bit on every entity, and you could keep a roaring bitmap of an entity's ancestors, and you could do bitwise operations to understand whether a given thing was visible. that was the principle. I built a proof of concept that showed it working. It turned out at scale that doesn't work at all because there's too many bit sets to look at, but it was the genesis of building a more sophisticated thing in memory. Did you want to talk about the cost node?
Yeah, so cost is the configuration that outperforms a single thread. Wonderful paper. Everybody should take a quick peek at it. But basically, it says, hey, if you fully utilize a single thread to the maximum capability you can on modern architecture, you can outperform many distributed systems. And they use PageRank as an example. So at Kevel, we call this one thread of awesome. Tim will let me have a second thread when I can show him I know how to use the first one. And that's been really a mind shift for folks at Kevel to maximize the use of a thread, maximize the use of a core, and we get there with this in-memory computation pretty much everywhere.
All right, so the last thing that I want to highlight is, kind of ongoing conversations that were happening in this time is the realization that we had to get off Redis, partly for the reasons I already talked about hitting its limits. We also realized we needed to break up what Heimdall was doing, where it was indexing add weights and add sets all in Redis, right? So there was a customer in 2018 that asked us to really expand our indexes, and we accepted because, we're a startup and like, hey, this is what the customer needs, let's do it. At the time we made that decision, I don't think we really understood the consequences, but it put a lot of strain on both Heimdall and Redis. So it became clear we really need to divide those things up and allow them all to scale independently. This last note, if you want to talk to this, Paul, but at the time, you were involved in doing a lot of tuning with Redis to actually make it work reliably when you're sending data from Virginia to Singapore. And so a lot of time spent in looking at replication protocols.
Yeah, so, for Tim, his analogy is working on Datomic and ideas from Datomic. For me, looking at replicated state machines and replication protocols, I could instantly see this vision of applying functions. In a couple of slides, we'll sort of see that come to life slide by slide.
Actually, that slide is
that's this slide right here. Perfect, thank you. So we're going to walk you through what we built here, sort of how this all works. But we're going to start with something a little bit more familiar. So perception and action inside of Clojure. And I'd like to thank Stu Holloway for writing my slides for me 14 years before I needed them. It's perfect. I owe him a drink. Oh, OK, it's Rich. It's Rich. Oh, even better.
Stu should have given you credit in his talk.
Perfect. So here we go. We have Clojure's time model. This should be familiar to most folks in the room. We live this life every single day. We start with some immutable value like a map. We apply a function to it like a soch. That gives us a new version of that map, a new immutable value. And that function application is what moves us forward through time. We can have as many observers as we want, party as much as you want. It doesn't impede our ability to apply a function and derive a new value. Right? So our read side is fully separated from our write side. Everything's great. Things are stable. Things make sense. I've got a view of the world that doesn't shift out from underneath me. Everybody get your pitchforks ready. I'm going to say that values maybe aren't the most important thing in this picture. I know. It's this deterministic atomic computation that's actually really, really important. That applying a function is what moves us forward through time on those stable values. Value semantics are one way to get there, and immutable values with pure functions are one way to get value semantics, but it's not the only way. So let's see how we do this in a distributed system. Oh, look, it's exactly the same. Perfect. Whew. Put the pitchforks away. All right, so we just recreated ViewStamp replication by Barbara Liskov in 1988, same exact model. Typically, when we look at distributed systems or replication protocols, it's always through node communication. That's what everybody wants to focus on, how the nodes pass those values around. But if we look at it through the lens of function application, we see the exact same model emerge. Right? In a replication protocol, I need a stable value, here version 1. I need to atomically apply a function to it, and I need to derive a new stable value, a new version, version 2. And the nodes in my distributed system, they'll communicate that function and those versions. But what we're going to do is be smart and be cloud native here. I'm going to take all that node communication and all the problems about node communication, I'm just going to hoist that onto S3. And instead, I'm going to spend all of my time focusing on what matters most, what those functions are, and how I'm going to apply them. Again, we have observers and processors here. The observers, we can have as many as we want. The more the merrier. Fully decoupled from our right side. Observers, we're going to put all of that load onto S3. Thank you, AWS, for infinitely scaling out my read side. Perfect, and it doesn't impede my ability to apply a function and make a new version show up. All right, so let's dive a little bit deeper now that we have that model. We call this system value change streams at Kevel. We'll go through this whole thing, but this model also has identity as a first-class thing. We call it a ref in our system. And actually, a ref will get a dedicated path inside of our S3 bucket. So you could see sort of the full timeline of that entire ref play out. We have values. Values can be arbitrarily large. They can be any size you want them to. Unlike some other very common stream-oriented systems that people build with for distributed systems today, we're not limited by size. So we pick the size that works best for your system. But sometimes you don't want to ship the whole value. You don't want to use the whole value. Imagine you had a map with 100 million keys in it, and then you're just going to associate one more thing. That associ is very tiny. The delta is exceptionally small. So maybe we should focus on the deltas. Deltas in our system are fully versioned. Everything in this system, fully versioned. And we'll talk about why that's important here in a second. So we have reified deltas. They're certainly more efficient. And given a stable value in any number of deltas that are versioned, you can derive a new value, right? You know how to build that whole system up. In value change streams, you can have values or deltas or both, and in any format. It's a fully extensible system. It's semi-self-describing. It's quite flexible. In many of our systems, we use MessagePack and LMDB. Some of those systems that use MessagePack will probably use a zero copy representation in the future, but quite flexible. You can do whatever you want. This makes a lot of sense so far, hopefully. All the values and deltas are coordinated using hybrid logical clocks. And this is where it maybe gets a little weird. The more traditional choice might be a Lamport clock to version everything. But with hybrid logical clocks, readers can create read transactions across any number of values, any number of refs, and across all partitions, coordination-free. So here I am an observer. I can go to any S3 bucket. I can create my own read transaction across whatever data that I want. It's fully stable. That all works. So hybrid logical clocks give us that capability, these coordination-free read transactions. Systems, the consumers of these things, they only use the values that they need. Right? We don't have to replicate all data to all systems all of the time. We can sort of choose partially how we want to replicate the data based on the needs of those systems. And value change streams have a consistency model. We use strong causal plus consistency, also called causal convergence consistency. That's sort of the best of all worlds, in my opinion. We can have the argument later. But things that are causally related are ordered that way. They're logically ordered that way. But you get this scale of eventual consistency. So everything in this system is fully versioned. We have a differential delta style replication system. We have a partial replication system. And we can have these enormous coordination-free read transactions. And the combination of all of these pieces are sort of what make value change streams unique. So let's look at how this works in practice. This is sort of a more realistic view of how a system runs in the real world. Here we have service F. Service F does some computation in memory. It's going to consume these deltas out of one ref called source. It incorporates that into its in-memory representation. Maybe it has to build some special indexes to do its calculation. It does a deterministic calculation, some deterministic atomic computation. It has an output, a stable output. That's going to get versioned, and it's going to emit a delta into another ref. That's that V1, V2 delta in the destination ref. Cool. At some point in the time, or in the future, it's going to say, hey, I want to take everything that I've calculated in memory and also make that a stable value. And value change streams, we call that a checkpoint. Pretty typical term in a distributed systems setting. So it writes its checkpoint to another ref. Checkpoints aren't really special other than that they're used for an in-memory representation. They're a value just like anything else. They get version with an HLC just like anything else. Consumers, observers here, can make a read transaction that includes checkpoints. Things are great.
Not that these diagrams were drawn to show operational order, but it does occur to me that really the checkpoint should be after the delta.
Yeah, there's no notion of time in this. It's like a snapshot of all operations
These are just
that occur.
all the parts that happen, yeah.
Yes. Well, you know, here we have another service called Value Producer. Value Producer consumes deltas out of one ref and emits values back into that same ref. Again, all versioned. Everything in the system is fully deterministic. Everything in the system gets versioned.
I want to come back to a point you said on the previous slide and related to Value Producer, right? The goal of this is we have some consumers of these things that just want whole values periodically. They don't care about high frequency updates, and they want to be able to look up anything in the entire value. There are other systems that need to know granular change, right? And that may be the only thing they need to know. That's where the duality of reified deltas and full values is super helpful.
Checkpoints are great for another use case here, as that bullet point suggests. Imagine you want to instantly resume a service. Well, you don't want to have to build up everything that was in memory. You don't want to have to reprocess all of those deltas. Well, a checkpoint just restores you to a point in logical time that's fully stable, again, fully deterministic, fully versioned, and then you can continue processing from that moment. Let's jump to the next one. So this is implemented using pretty simple repeatable patterns. You use them everywhere. Once you have that mental model of how value change streams work, there's really only two jobs to do. We have processors. Processors, as we saw with service F, they consume deltas typically. They incorporate those changes into memory, make some deterministic computation that they have to make, and they produce a new value, either a new full value or a delta. If time moved backwards, we can detect that because everything's versioned, right? If it detected things shifted and it deterministic, well, we have causal consistency, so it would detect the version going backwards. Everything has to happen before a logical order. So it can skip information if it needs to skip information. That processor, again, puts the delta into another stream or the value in another stream, or a ref, and checkpoints as needed. Observers, that's where the party's at. Observers do this wonderful, beautiful retransaction across whatever they need to do. They grab the deltas, they grab the values, whatever they need to consume, and they consume it. And our system, as Tim was sort of showing our architecture from previous, you can imagine our decision engines at the edge all around the world. They're just going to be observers. They're just going to keep consuming data. They want a stable view of the world, and they're just going to run decisions. A query comes in, and I need to process that. It's pretty nice to have everything versioned, to have everything stable and immutable, because you can always do this cool trick, which is I want a stable view of the world, and then I want to atomically swap to the new version of the world. That should be familiar for all of the Clojure programmers in the room. This is no different than having an atom and doing, you know, a deref or doing a reset on that atom. We didn't just get here overnight, right? This looks like one gigantic leap, but we took a bunch of little steps along the way, and when we present it in these slides, you see the leap. So we started piece by piece. The first thing that we did was we implemented indexing as a processor. We wanted to see, can we just make values work? The indexing system, yes?
Well, I was just going to add, this was very much driven by, you know, we had these ideas in mind, but it was driven by particular pressures on the business. So we had customers wanting to do things with indexes that had already strained the system, and we had new customers coming in that wanted geodistance indexing. And so there were a bunch of reasons we needed to tackle the indexer, and we chose to use it as a test case for this.
Yep, so indexing used values. We just made a stream of values. We atomically swapped those values. We tried out how we were going to do versions. That was test number one, and it worked great. It's run for years, hardly any issues. Turns out immutable values work. You know? Wonderful. The next piece we wanted to do is, can we make this deterministic computation model work? Can we make the deltas work? And can we make some in-memory representation of data sets work? And we did that with Change Expander, which is where we handled the fan-out problem in memory. That's where we do this roaring bitmap index that we build, and we sort of store up memory inside of LMDB, and that's what we use to make checkpoints. It produced delta streams, so we got to test out our delta format there. What's particularly impressive is we reduced 400 Geffian machines, which used to do that fan-out with a queue, down to 3 machines when we initially released it, and we added 2 more partitions. So 2 orders of magnitude just by turning the problem to an in-memory computation problem. At this moment, Kevel adopted lightweight formal methods as a way to do this. It's quite difficult to engineer these always-on, never-fail systems. So we sort of adopted these lightweight formal methods, very similar to how the S3 team does it. There's lots of examples. We even had other talks that shared similar processes here. The next piece is we wanted to see how far we could extend this model. We wanted to sort of understand all the edges of this design. Kevel hosts master's students that are doing their master's thesis about some core industry problem that Kevel has. So they use us sort of as a little research test bed. We had one exceptionally bright student, Deanna. She wrote this beautiful thesis towards causal consistency in read-heavy cloud-native systems. If you think this is cool, you should definitely read that thesis. It's 170 pages long, so she's a master's student, but that's basically a PhD thesis. She got a perfect score on her defense. But we showed that through the history of all causal consistency systems, where this one sits, and we also tested its ability to work across multiple regions around the world by showing that you have a very interesting little trade-off between data staleness at read side and the latency across the entire system. And that it's fully configurable, which is a very powerful thing to be able to dial in. And finally, we uprooted the Redis tree.
Well, we're in the process of uprooting the Redis tree. So this is the architecture that we're at now. The main pieces are all still in here, but reconfigured. So I'm going to walk through this again like I did the first one. We still have the management database on the far left. There's a change data capture consumer from it called publisher, which is turning, it's not really the entire change history, but it will catch you up. So it'll tell you what things have changed and give you their latest state, which is what we really care about. So that's surfacing those as deltas. Those are being consumed by Change Expander, right? The thing that in memory is doing the calculation about what's visible and not visible in the ad set. From this point on, everything is built using value change streams. So that's emitting values into S3. Those are getting consumed by the scheduler. Scheduling was sort of a part of what Heimdall did about when it had to relook at ads to rebalance them. It was all queue-based as well. Heimdall still exists, but it's been converted into just an HTTP endpoint you can call, and scheduler is now driving the invocations against that. Scheduler writes ad statuses, meaning, what should the new balance weight be? Should it be taken out of the index because it hit a cap? Things like that. Again, into a change stream. Ad set manager is combining those 2 change streams, right? There's 2 sources of change in the ad set. One is anything somebody did with the API in management and any results of balancing. So changes there would be adjusting balance weights or, as I say, removing something because it's hit a lifetime cap. That in turn is producing a value change stream of active ads. That's being read by the indexer to understand what it needs to add or remove or change in the index. Both those streams, the indexer stream and the active ad unit stream, are being consumed by the engines. So all of the data distribution is now, again, you can see from the labels, right? Distinct reads and writes, all via S3, all the way out to the edge.
One second before you jump to the slide. One thing to call out, again, everything's version, everything's deterministic. It works like this. All of our reads are separated from our writes. We can time travel the entire globally distributed system, right? We sort of know how everything logically flows forward. So if we detect a bug on one engine and anywhere in the world where we're deployed, We can look at the versions that were used on that engine at that moment in time, restore them all locally on a single box, and time travel that system forwards and backwards to constantly replay that bug.
Yep, and we could trace it all the way back through versions. Ultimately, I don't know if this is wired up yet, but ultimately, it'll tie to 2 critical logs, events that are happening in Balancer, like, hey, the Balancer made a decision to remove this ad. Why did it do that? And also the audit log for the management API, right? This thing changed. We want to be able to say this decision, like, why was this ad not selected? And be able to walk it back through versions all the way to, hey, it was because somebody on your team made this API call to our management system and turned that off, right? So the traceability is key. All right, so key aspects of this model. We've already talked about separating reads and writes so they scale independently, separating compute and storage so they scale independently. We can add concurrency inside these functions. That process Paul described is downloading a delta and processing it in memory and updating a checkpoint, right? You can do that in parallel across multiple partitions within a single process to increase concurrency. We've talked about the fact that because we're producing values that you can fetch from S3 and just run with, it's super reliable. I want to make the point, some people look at this model and say, well, it seems stateful, right? You're doing this stuff on a single box. I would still argue these things are stateless in that they take all of the critical state in their checkpoint and offload it. So if one of these boxes fails, we replace it with another one that simply picks up that checkpoint value and continues. And you could run them hot, cold, or hot, warm, or even hot, hot if you wanted to, right? So it's no different than the Datomic transactor in that sense. Throughput is high, it is batched, but compared to the backups that used to occur in the old system, like Geffian storms, the processing through here is substantially better. We already talked about everything is versioned. And then I added one more bullet to this slide late in the day. I don't know if Paul saw it, but it's because I heard Rich, his voice from the past, saying, engineers know the benefit of everything and the cost of nothing. And I said, I can't stand up here and give you 8 bullets of the positive without something, the negative. Not even negative, just a challenge, right? I will say about this, it has been an interesting path. It's a pretty different way to build, right? And there have definitely been conversations internally about, should we really be working at this level? Should we be trying to use off-the-shelf solutions and focusing more at the application level? Because down here to make this work, right, we care deeply about what is the fastest way to move data to and from S3? What is the optimal size of that data to get the best throughput? How should we encode information in there to ensure that the costs of packing it or unpacking it are as minimal as possible? Like, you have to really be thinking at a pretty low level to build this way. Our goal is to get that done across the system, and then at the heart of each of those critical components, I mentioned there's sort of 2 main decisions being made for balancing and decision making, to actually have that be a true function. And maybe someday challenge Conway's law and say there's one team that maintains these underpinnings and there's another team that maintains those functions. You can think of it sort of conceptually as similar to what Lambda would do for someone, except it will be completely specific to our problem, right, and how we have to shift data around. There's a couple other really eye-opening aspects of this that are interesting. Paul already pointed to one, right? I talked about the fact that we have to scale our decision-making as big as our customers get, and some of them get really big. And this model puts the burden of that on AWS. We will scale as large as S3 and EC2 capacity in a region. And it takes us, essentially no effort to do that, right? They just take care of it. It's no effort and no cost. It also means, we didn't really talk about the data flowing out of engines, but there are logs of what the engines are doing that are already delivered via S3. This means the input to the engines will be S3. This makes it, it opens the door to deploy engines in a cloud prem model where they run inside somebody else's AWS account. And that's really interesting from a speed perspective, right? Because it can be as close as possible to their servers without having to get VPC peering set up. And it also helps with privacy, right? We really don't want any data about customers that belongs to our customers, right? Their users. Optimally, none of that stuff would flow to us. We don't want it. We don't do anything with it. It belongs to you. So if we could get there, that would be great. The third thing is we can use S3 replication to move checkpoints to other regions. And because we can use them to restart services, this gives us the basis for doing cross-region disaster recovery. Like I mentioned, the fact that there were Lambda challenges in US East 1. I had a very disconcerting evening. We were actually in Europe, and we were flying into Paris, and we landed at the airport, and the first thing on the phone was, Lambda's not working in AWS, and what's happening with our system? And we spent the evening trying to figure out what was going on and when it would recover. I want, in that circumstance, to be able to pull a giant Frankenstein switch and relocate the work to another region. But we don't want to pay the price, as we would have had to with Redis, of maintaining an entire separate Redis tree ready to go, because you can't build it very fast. This opens the door to say we have replicas of all of these checkpoints available elsewhere, and we can move work there and recover the state of this entire process machine, right, in a relatively short order. So that's a thing we're hoping to get to next year. And then one last thing, because as Craig likes to point out, this is how I tell people I'm a CTO without telling them I'm a CTO. There's another interesting aspect of this to me. When I was a young engineer, I didn't think at all about what things cost. If someone asked me, I'm like, I don't know, I just build the software, right? At the other end of my career, I think about this all the time. And the reason is we're a SaaS company, right? And the value of SaaS companies derives from the fact, the investment hypothesis in a SaaS company is the idea that you can add customers and your cost do not increase radically, right? The cost of adding new customers is linear and a pretty slow ramp. So basically, our goal, how do we prove that we can do that? And there's 3 metrics that matter that we look at every all hands meeting, every quarterly meeting, every board meeting, right? Annual recurring revenue. So how much money are you making? Net dollar retention. So how much money is coming from customers you've had for more than a year, so we can show that we're not just churning through customers. And gross margin. And it's really gross margin that is relevant here. Like, to get a SaaS valuation, right, you want to maintain a gross margin of 80% or so. And I should even back up, right? I don't know how many of you spend a lot of time thinking about how companies get valued. But when you buy a company, in general, you pay some multiple of revenue. If you buy a consultancy, it's typical to pay 1 times revenue, because you're basically just buying that consulting business, the hours people work. Light manufacturing, it's like 1.5 to 2. SaaS companies, it used to be higher. Today, it's like 10 to 11, maybe 12. So there's a lot of reasons to build a SaaS company to show that you are one. And part of what you need to show that you are one is margin. And one of the interesting things about this model, so what does margin include? It includes revenue minus cost of goods sold. And cost of goods sold is what you're paying vendors, so AWS and Datadog and a couple other folks for us, what you're paying your support team, and what you're paying for DevOps. So I asked that question earlier, how many of you run your Kubernetes cluster? And everyone's hand went down. There's a team somewhere in your company of 30 people, 50 people, whatever, that do that. They all go to COGS. So we are purposely making a choice to do more complicated engineering up front to keep those costs in R&D, because the operational costs, based on our experience to date with this model, are substantially lower. Right? In the first 6 months that we worked with a new index system that was being built this way, right, with values delivered this way, it accounted for like less than 0.5% of issues that were raised against the system. So there's real value, I believe, in this approach of doing the work in R&D, taking on these problems, and not relying on a lot of the off-the-shelf technology that promises to solve all these things, but where you need a lot of operational capacity in order to do capacity planning, migration, add nodes to clusters for storage, all of that stuff. Like, we have given that all to AWS, right? And this is a big part of why. All right, I just want to shout out to the team that's been actually working on this. There's 5 of them sitting right there.
Right over there.
So if you see anyone here with a Kevel badge on and you have a question, like ask any of us. All right.
Thank you very much.